Most people have heard of Schrödinger's cat. A cat in a box with a radioactive atom. If the atom decays, a mechanism kills the cat. Before you open the box, is the cat alive, dead, or somehow both? Here is what most explanations miss. Schrödinger invented this scenario in 1935 not as an example of quantum mechanics, but as a reductio ad absurdum against it. He was mocking the idea that superposition applies to macroscopic objects. The cat was supposed to show how ridiculous the theory was. Instead, it became its mascot. Superposition, in its technical meaning, is this: a quantum system can exist in a combination of multiple states simultaneously, described by a wave function that includes all of them. An electron spin can be up and down at once. Not alternating rapidly. Not unknown to us. Actually, simultaneously, in a mathematical superposition where both possibilities coexist with specific amplitudes. When you measure it, one outcome appears, with a probability given by the amplitude squared. Before measurement, there is no fact of the matter about which state it is in. So why doesn't the cat seem to be both alive and dead? The answer is decoherence. A quantum superposition is fragile. The moment a quantum system interacts with its environment, even just one air molecule bouncing off it, the superposition entangles with the environment. The quantum phases that make interference possible wash out into the noise of trillions of environmental interactions. What remains looks, for all practical purposes, like a classical probability, either alive or dead, not both. A cat involves something like 10 to the 23 atoms, each interacting constantly. Decoherence is essentially instantaneous. Superposition is not just a curiosity. A quantum computer stores information in qubits that can be simultaneously 0 and 1 in superposition. When you run a quantum algorithm, you exploit the interference between all superposed states at once, pruning wrong answers and amplifying right ones. For certain problems, this is exponentially faster than anything a classical computer can do. The challenge is maintaining coherence, keeping qubits isolated from their environment long enough to compute. The entire field of quantum computing is, in a sense, the engineering problem of protecting superpositions from Schrödinger's environment. The deepest problem in quantum mechanics is called the measurement problem. When you measure a particle in superposition, you get one definite answer. The superposition collapses. But quantum mechanics does not tell you when or why this happens. The equations evolve a wave function smoothly and deterministically. Nothing in the mathematics marks the moment of collapse. Many physicists get around this by just not asking. Shut up and calculate, as David Meerman put it. Others propose the many worlds interpretation: all outcomes happen in branching parallel histories. Or decoherence is the answer. Nobody agrees. The measurement problem is open. Schrödinger wanted to show quantum mechanics was absurd at scale. He got more than he bargained for. The cat thought experiment did not kill the theory. Instead, it sharpened the question: at what scale does quantum behavior become classical? Decoherence says, very quickly, for large systems. But the transition is not in the equations. It is in the complexity of entanglement with the environment. The cat is not both alive and dead. But the atom that might have triggered its death? That atom, isolated from the world, has no definite answer until something irreversible asks.